And we're back for today for 11.4 day 2, guys. There's a hole in my function, so we're going to check out the holes again here. But before we do, we are going to have a relatively short video today on day 2. You're going to finish the last 3 graphs and your limits page on the last page of your homework. Tomorrow we're going to do some applications. Thursday, chapter review. Remember, it's live day on Thursday. If you have questions, that's the time to ask Mr. Myers or myself questions on what's going on, and you're going to have to submit 11.4, 11.5 try on your own, and your chapter review before completing your chapter 11 summative on Monday, this coming Monday, April 26th, and that will shut off that night, okay? So before I get rolling here, I have my Kruger's fail-safe rules, steps to graph any rational function, which were not in your notes yesterday. Hopefully you jotted them down, and if you don't know these, I hope you hit pause and jot them down because they work beautifully. And all we're going to do here today is we're going to do 2 problems, and I'm going to follow these the same exact way that I did yesterday. Kruger's first rule is completely factor both numerator and denominator. Notice I gave that x minus 5 a hug. Nothing factored, so that is an entire factor down there. It all goes because there's subtraction. Well, up here in the top factors, I believe it factors to, looks like about a x minus 5 to an x plus 3. And what I'm going to do here is I'm going to state my domain now, remember. State my domain, it's all real numbers, x except 5. And after I state my domain, I will, look at that. Those x minus 5s reduce out. And wouldn't you know it, it's going to give me the green light that this function actually equals x minus 3 over 1. Now, do I have to put something over 1? No, I do not. And so all I'm going to do is I'm going to call it that whole thing reduces to an x minus 3. And that should look kind of particular to you. It should look a little funky. Not really funky, but it should look good. And because that x minus 5 reduced out, I have a hole at x equals 5. And I got to find that hole. My hole is going to be, that's a bad 5. My hole is going to be at 5 comma what? Well, it's going to be at 5 comma, well, when I put a 5 in here, 5 minus 3 is going to give me 2. So I'm going to find that hole in my function. It's going to be over 1, 2, 3, 4, 5, up 2, or what did I do? Hold on, that's an x plus 3. Whoa, come on, Kruger. That's a plus 3, which means that hole is a little bit different than that. That hole, oh boy, I hate making mistakes. It's going to be 5 at 5 plus 3. It's going to actually be at 5, 8. So I'm going to go plot that hole at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, my hole's way up there in the top. Well, hopefully, yeah, I can get up there a little bit further yet. And what I'm going to do, I'm going to move my graph down a little bit, sorry. Okay, moved it down because I know what's coming, so I moved that little bugger down. And all I really need to see is my reduced function now. And is there any way to make the denominator of that reduced function? Remember, that's over 1. There are no vertical asymptotes. That x minus 5 that started out, it reduced, so it's not a vertical asymptote, it's a hole, which means I have none here. Okay, there are none. How about horizontal asymptotes? Well, the degree of the top is 1, the degree of the bottom is 2. What happens when the top is bigger than the bottom? There are none. Oh, that happens, okay? My y-intercept. Well, I'm going to find my y-intercept by plugging 0 into my reduced function, and that's going to give me a 3. So 0, comma 3, 0, 1, 2, 3. I'm going to plot that little bugger. And how about my x-intercept? Well, my numerator can be 0, because if I put a negative 3 in there, I'm going to get 0 out, right? So 1, 2, negative 3, 0. Now, don't be confused by this. Look at what our reduced function looks like. It looks like a line, doesn't it? And it is a line. Our reduced function is a line, so our graph is actually going to be a line with a hole in it. Okay, it doesn't have to be the branches. Notice I said yesterday's, and every time I've said, you have a piece of the graph on both sides of all vertical asymptotes. I don't have a vertical asymptote here, so I do have two pieces of the graph. I got a piece of the graph on one side of the hole and the other side of the hole, but they're not branches. This whole graph is aligned with a hole in it. So why don't we try this second one here again? Well, let's look. Let's take a little handy-wandy here. Well, let's try to factor that top, x plus 1. Well. X and x, my signs have to be the same, right? So what am I seeing here? Well, x plus 5, can I put a 1 and a 5 here? And that's going to give me 6 in the middle. And if I switch my 5 and my 1 here, that still gives me a 6 in the middle. What does that mean? Well, what that means is this thing does not reduce, okay? It's as reduced as it goes, so it doesn't factor. So I'm going to state my domain. My domain is all real numbers, x, except that pesky little -1 right there. And I'm going to come to my -1, and I'm going to graph that little booger. There he is. And I'm going to move my graph down again because I know I'm going to have to, so give me a second. And because that pesky little bugger didn't reduce, I forgot to write my x equals -1 as my vertical asymptote. How about my horizontal asymptote here? Well, when the degree of the top is bigger than the degree of the bottom, we have none. Okay, there is none. However, what do you notice? I did this before too, and I just didn't do them. There's nothing reduced. I had no holes. Well, the top is exactly one more than the bottom. That means we've got a slant asymptote. Remember how we find our slant asymptote? We pull our coefficients off. So I got a 1, and a 5, and we divide it by what makes this denominator 0. So I'm going to divide out a -1, and we drop like top. I get a 1, I get a -1, I get a 0, I get a 0, I get a 5. We synthetically divide out. We do not care about our remainder for a slant asymptote, and we see our slant asymptote is going to be of the equation y equals x plus 0. I don't need that 0, but so it's really just y equals x. Hey, that's my identity line, so I'm going to graph. I got a y-intercept of 0, slope of 1, so I can make all these points coming up. And I can make all these points coming down to graph my slant asymptote. So I know I got my, ooh, that's bad. That's a bad slant asymptote. I'm going to try to keep him in there like this as best I can. And there's my slant asymptote. And then from there, I'm going to find my y-intercept. Well, my y-intercept is putting a 0 in for x. And when I put a 0 in for x, I'm like, you're gone. You're gone, you're gone, and I have left with 5 over 1, so that's 0, 5. 0, 1, 2, 3, 4, 5, and I'm going to plot that 0, 5, and I scribble those out in my mind so I don't have to do it again. And then my x-intercepts, ooh, that's when the numerator equals 0. Well, my numerator didn't factor, ladies and gentlemen, but my x squared plus x plus 5 still does have the capability of equaling 0. And just because it didn't factor, well, remember, that just means we need to use the old x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a, because we can solve non-factorable quadratics with the quadratic formula. However, I highly recommend you look at this first, because if that's a negative number, they're imaginary, which would mean I do not have any. So whenever I do the quadratic formula, to be completely honest, that's the first thing I do. And I say 1 squared minus 4 times 1 times 5. And I see this is going to be 1 minus 20, or negative 19, which means they're imaginary. So I know I'm going to have none here. So I don't need to worry about that. And just because it doesn't factor, please don't make the assumption that they're not going to be any, because I think Mr. Myers has been talking, and we might make sure you have a couple of those that you're going to have to factor. So don't just automatically say it's not going to be there. And then now I'm going to graph my branches. And I can see one branch, okay, I'm never coming down to the y-axis or to the x-axis, so I know this branch is going to come in off of that one, and it's going to end up coming up. And anytime you have a slant asymptote, your branches of your graph are always going to be directly across from each other or kitty corner. So I know this piece is going to be down here. And if you really wish to find an accurate point, you're welcome to. But again, when we're grading your graphs, guys, we're grading are your vertical asymptote in the right spot, your horizontal in the right spot if it has one. If it has a slant asymptote, is it graphed in the right spot? And that your x and y intercepts are in the right spot, and that your branches are in the appropriate sections of the graph. Beautiful graph you got right here. You don't have to spend all the time in the world on them, all right? So then last thing we're going to do is in summary, we're going to look at a hole versus a slant asymptote. Well, right away I can see this is not possible to have a slant asymptote because the top is smaller than the bottom. This is going to have a horizontal asymptote at y equals 0. But as I factor it, this is going to have a hole at x equals -4. So I would find my hole by plugging -4 into my reduced function of 3 over x minus 2, which is going to give me my 3 over -6, or -1/2 would give me the location of the hole there, all right? Number 2, well, right out of the blocks, number 2, I can see this is not going to have a slant asymptote because the top is smaller than the bottom, so it's going to have a horizontal the same way this one does. But when I factored the bottom, notice those x's reduced, so I will have a hole at x equals 0. And to see the hole, we write our reduced fraction, and then we say we plug our x value into our reduced fraction to get 6 over 3, or my hole being at 2. Okay? Now, when I look at number 3 here, well, number 3, it sure looks like I'm going to have a vertical or a horizontal, a slant asymptote, because the top is exactly one more than the bottom. But when I factored this dog, notice my factors reduced, so I had a hole at x equaled 5, I believe it was. And I could find that hole was at 5, 8 in that problem. And my reduced function was x plus 3 over 1. Well, now my top is not exactly 1 mark. Because I don't have a variable of x in the denominator, I cannot have a slant asymptote. So by this factor reducing, not leaving a value for x or a variable of x in the denominator, that eliminated my slant asymptotes opportunity for me there. And then this last one, when I looked at it, okay, this looks like, it originally looks like it's going to have a slant asymptote, okay? We tried to factor the top, but the top didn't factor, so then we said, oh, because it didn't factor, nothing will reduce, so there was no hole, okay? If your fraction does not reduce, it's not possible to have a hole. And because the top was exactly 1 more than the bottom, we used our synthetic division of 1, 1, 5, and we synthetically divided out what made the denominator 0, and we found that we got here, and we initially, well, for slants asymptotes, we ignore our remainder. And remember, this was an x squared plus an x plus a 5. And when we synthetically divide, we take it down a notch, which means this is an x, which means that x is now my constant, which means that constant is now my remainder. We ignore our remainder, and we say x plus 0, and we slap and chap a y in front of it, and that is the equation of our slant asymptote. And that's how we go with that. Last one, all you got to do, guys, is you got to finish up those last 3 problems in those infinite limits, finding horizontal asymptotes and stuff in the graphs, and we are done. We will be back tomorrow with some applications, except this is supposed to be a big fat 4. Finish 11.4. Try on your own. We are out. These are try it on your own problems if you got help or if you need help. Hey, have a great rest of your day, guys.